All right, guys, this is Mrs. Lyons, and this video is on average atomic mass. And we're going to go through how to carry out calculations when you're given the percent abundance and the mass of different isotopes. Okay, so just some notes to fill in before we get into the calculations. First of all, an isotope is an atom that has the same number of protons and a different number of neutrons. All right, and the properties of the element are almost identical. When we get into nuclear chemistry, that's where we would find the differences. With their nuclear chemistry or nuclear reactions. All right, so here's an example. We've got the three isotopes of magnesium. Okay, we've got magnesium 24, 25, and 26. So the first thing that you have to do is look at your periodic table and figure out what the mass number, atomic number for the different isotopes is. So we know atomic number, so magnesium is element number 12, okay? So the atomic number is 12 for magnesium. And then that tells us that there are 12 protons, okay? If it doesn't have 12 protons, it is not magnesium. This also tells us, right now we're talking about neutral atoms, so the number of electrons is the same, okay? And then the mass number, if we don't give you a mass number, if we don't give you a different number in the problem, you're just going to use the mass number that comes behind the isotope in the hyphen notation. And remember the mass number, so I'm going to write 24, 25, 26. The mass number is the number of protons plus neutrons. Okay, so that means in magnesium 24, there are 12 neutrons. In magnesium 25, there are 13 neutrons. And in magnesium 26, there are 14 neutrons. And then we're going to write the nuclei symbol just to practice. And remember, that's always going to be the element symbol. And then we have the mass number on top, atomic number on the bottom. So 24, 12, 25, 12, and 26, 12. Okay, now the average atomic mass of an element is the atomic mass we see on the periodic table, and it's the decimal number. Okay, and what the average atomic mass is, it's a weighted average. Okay, based on the masses of the different isotopes. Okay, on the Earth. So the average masses of all of its isotopes found on Earth. Okay, so when we calculate, and this was just an example to look at how we count particles, okay? When we calculate, we will look at a problem, and sometimes you would use the mass number, but other times we'll give you an exact mass. And in this case, we give you an exact mass, okay? So what we do is we want to find the average atomic mass of chlorine, okay? So this says that chlorine 34 has a mass of 34.97, chlorine 35, and that makes up 75% of all of the chlorine atoms. And then chlorine 37 has a mass of 36.97, and that makes up about 25% of all the chlorine on Earth. So what we do is we're going to take the isotopes. So the first isotope, the mass is 34.97 AMU, and we're going to multiply that by the percent abundance, so 75.77. And then we're going to combine that. We're going to add it to the mass of a second isotope. So the mass of the second one is 36.97. and we're going to take that times 24.23 is the percent abundance. And then we're going to do this math, and then we're going to divide by 100. Okay, so I'm going to use my phone as my calculator. All right, so the way that I plug this into my calculator is I plug it in and I use parentheses. So I would do 34.97, 34.97 times 75.77, okay, plus 36.97 times 24.23. And then I'm going to divide that whole thing by 100. And I get, as an answer, 35.4546. Now, if we look, we have 4 sig figs in all of our numbers. So the average atomic mass of chlorine is going to be 35.45 AMU. And if you look at your periodic table, which I don't have a periodic table handy right now, believe it or not, but if you look at your periodic table, this is the decimal number, or really close to it, that you would see for chlorine. So hold on, I have my handy dandy phone periodic table. And if you look at chlorine, the average atomic mass is 35.45, okay? So it should come out really close to what we see on the periodic table. All right, so now we're going to do magnesium. And like I said, sometimes we might just have you use the mass numbers, but more times than not, we're going to actually give you a true average atomic mass, okay, or at mass of that particular isotope. All right, so this says that for magnesium 24 has a mass of 23.98504, lots of sig figs, and the natural abundance of that is 78.99%. Okay, I'm going to add that to the second isotope, which has a mass of 24.9858 times 10%. And then there's a third isotope, which has a mass of 25.9829, and the average abundance of that is 11.01. Okay, do all of this and divide by 100. So let's see what we get. And let's just look, while I've got my periodic table here, what we expect. So if you look, the average atomic mass of magnesium on the periodic table is 24.305. So let's see what we calculate. Okay. All right, so let's see. Let's see if I can move this up here. Here we go. So 23.98504 times 78.99 plus 24.9858 times 10 plus 25.9829 times 11.01. And if we divide that by 100, we get 24, and we're still just going to use 4 sig figs because our percentages only had 4 sig figs, so we would get 24.31 AMU. Okay, so that's kind of how you look at calculations. I want to flip over. I think there are a couple of, yes, I want to just kind of show you if we're thinking about this conceptually, okay, what that means. Okay, and this first question on page 11 kind of addresses that. Okay, and we can use this this instrument called a spectrometer. And what the spectrometer does is it analyzes a sample, and you get a graph that shows you the different isotopes and their relative abundance. Okay, and we can calculate from this if we wanted to, but we can also do something else. We can look and we can see the different average atomic mass, or the different isotopes, and we can see their relative abundance. Okay, and what we will, the conclusion we want to draw is our average atomic mass is going to be affected by these natural abundances. So for zirconium, the largest isotope in terms of abundance is zirconium 90. Okay, and it's got a little bit over a 50% abundance. So if I were to say to you, don't use math, okay, but I want you to calculate, or I want you to estimate what the average atomic mass of zirconium would be. And I might say it's probably going to be greater than 90, maybe somewhere between 90, if a rough estimate, I'm going to say between 90 and 91 or 90 and 92. So let's look at if we actually calculate that, what we find. Okay, so we've got, 5 isotopes. And in this case, notice we don't give you exact masses, we just have you use the mass number. So if I'm doing this, I would say that zirconium 90 has a mass of 90 times 52.3. I'm going to add that to the isotope 91, which has a natural abundance of 14. Isotope number 3 has a mass of 92 and a percent abundance of 15.7. Zirconium 94 has an abundance of 15.6. And finally, zirconium 96 has an average atomic mass of 2.4. Okay, so now if I do this math and I calculate this all out, let's see how close my estimate is. All right, so, whoops. Okay, so I'm going to do 90 times 52.3 plus 91 times 14 plus 92 times 15.7 plus 94 times 15.6 plus, finally, 96 times 2.4. All right, so let's see what we get. 9,000, oh, I've got to divide by 100, divide by 100. And my average atomic mass comes out to be 91 point, and this says what? To 3 decimal places. So 91.222 AMU. So my estimate was pretty good. I probably should have estimated between 91 and 92, but hopefully you can see kind of the idea here is whatever the most abundant isotope is, your average atomic mass is going to be close to that. So you should not only be able to calculate, but you should be able to look at a graph and or just look at numbers and be able to say, oh, I think that average atomic mass is going to be close to this or that. Okay, so hopefully, and there's a whole bunch of practice here that you're going to be able to do. So take a look at that. Check out the video. You can come back and watch the video again if you get stuck. But have a great day, and I will see you in class.